when you see the alkyl halide on the one side, the reagents are given. I mean, it can be written on the top of the arrow or the bottom of the arrow. It doesn't really matter the location of where they are. But anyway, the point is this KCN, that's the reagents, and then we got the alkyl bromine there. So you may think that the KCN is actually the salt, potassium salt of the cyanide ion. That's the one. So when that happens, the cyanide is a nucleophile. That's going to make the reaction to this carbon, kick the bromines out. And then this is the dashed. What that means is it's a stereochemically defined carbon. So when you see that, you got to be careful of the stereochemistry. But one thing that I want to show that is, yes, this one bromine is going to be replaced by the cyanide. So you get that. But not only that, this dash change the wedge because the cyanide attacked from the top side because that bromine sitting on the bottom side, so cyanide attacked from the top, bromine leaves the other way, so it's gonna stay on the top side of the molecule. What you don't want to write it out is any of like this. Solid line means that you don't know the stereochemistry, so that's not correct. And then reserving the stereochemistry is also wrong, so those are the bad. And not only that, using the whole thing, wrong things like the KCN, looks like the whole thing becomes a nucleophile, not the whole thing. That's a potassium salt, the cation. So that doesn't mean, that's not making a texture of this carbon. So that is also bad. So that's what we just talked about. I just wanted to hit. And then now, you know these things. I hope that you didn't forget about the Fischer projections, right? Fischer projection means that these horizontal lines are actually wedge line, right? And then these vertical lines are dash line. But you can still make the reaction wrong in the Fischer projections. This is a styrolate. Sulfur is a negatively charged. Sodium is just a positively charged countercation. That's a nucleophile, not this. That makes an attack to this carbon, kick the bromide, has to happen from the opposite side, same way. So when that works, where are we going to put the cyanide? Cyanide on the opposite side. So this is where the cyanide goes, and this hydrogen basically move to the other side, come over here. So you still can use the Fischer projections to draw the answer. That's totally fine. Or if you want to convert it to regular structure line with drawing with a wedge and dash line, that's fine too. It's just that this one's more convenient. That's pretty easy question in my opinion. But I want to think about top one, A. We've got several choices here. Okay. One, if you look at here, we got two reagents are given. One is a methanol, the other is a sodium methoxide. This can act as a nucleophile, that can act as a nucleophile. So we have two different nucleophiles in the system. Not only that, this carbon having an iodine also have a chlorine. We got two halogen there. And then it's a stereochemical defined. So what would happen if you treat that together? It's going to be substitution reaction. We only talk about substitution reaction. Later on, it's going to be multiple more possibilities. But right now, just the one reaction. So we know it's going to be substituted. But which one's going to be substituted? By what? Right? So we got two different nucleophile, we got two different halogen. If you're going to guess, it'll be probably quarter. Right. So that's kind of the things we need to talk about. So if you don't know what to do, let's just go back and think about what SN2 reaction requires. SN2 reaction requires strong nucleophile, right? Strong nucleophile make the SN2 reaction goes down. So we got two reagents are given. One is a sodium methoxide, the other is a methanol. So between these two, which one is going to be a strong nucleophile? So that question now goes, what makes a nucleophile strong? Higher electron density, right? You need a higher electron density to make a strong nucleophile. Is a conjugate base forms a more strong nucleophile, or the neutral form is the most strong nucleophile? So that's kind of the things that is something we are talking about here. That's a or negatively charged, because sodium is a countercation. These are conjugate base forms of the methanol. So that oxygen having a negatively charged, this oxygen is a neutral. So we've been talking about most of the time conjugate base forms become a stronger nucleophile because it has a higher electron density, being a negatively charged. So I hope that you choose the top one, that's a stronger nucleophile, not the bottom one. And then I want you to think about that when we classify the nucleophile, neutral alcohol, water, we consider very, very weak nucleophile because the lone pairs of the neutral alcohols are very tightly bound to the nucleus. They don't really go for the substitution reactions. So this is a strong nucleophile, not that one. That's actually sold here. But that one, now going for the reaction with this carbon. Now the second question comes along. What is going to lead? Is it going to be substituting the chlorine, or is it going to be substituting the iodine? That's the question, right? And then depending on which one makes it lead, you get the different stereochemistry. There's kind of a multiple things put it together. So anyway, so this is a carbon that makes an attack by the nucleophile. So that attacks. The question is it going to make an attack to this carbon this way, opposite side of the chlorine, and then kick the chlorines out? Or is this going to be attacking from the opposite side of the iodine and then kick the iodines out? That's the question. I mean, it looks like it's attacking the same carbon, so we're not going to get the nucleophile going to different carbon. But the problem is, which one is going to be kicked out? Or both going to be kicked out in the same way, so you get the 50-50 mix. Well, clearly, it's making a different things lead, right? It's going to make an attack, but it's going to make either chloride lead or the iodine lead. So leaving groups. We talked about these going to be leaving and it makes an iodide. That's going to be leaving as a chloride. Which one is going to be that more stable? And that's the one that's going to be leaving out better. Right? Is the iodide the better leaving groups, or the chloride is better iodide? I mean, it's not. I'm not saying that chloride is a bad leaving group. Chloride is a good leaving group. It's not just iodide is a much better leaving groups. I mean, differences are probably a little subtle, but iodide having a huge number of the electrons in there, and then it's going to be left out more stable. So iodide is actually much better leaving groups. I mean, not much better. It's a little better leaving groups than chloride. So we are expecting this nucleophile, not this one, right? I hope that I established that one at least right now. But this one makes an attack, opposite side of the iodide, and then kick the iodine groups out. So you get this nucleophile substituting here, iodine is gone, chlorine still in the product. I would expect that would be the major product. I mean, you may get the other one, attacking the carbon, make the chlorine lead. That will be the minor products, in my opinion, because it's not bad leaving groups either. I mean, both are pretty good leaving groups. It's just iodine leads better. So if you may expect that both happening, but you get more of these forms rather than going for this one and then kick the chlorines out. So, and then you really want to make sure that you show the stereochemistry correct, right? So this is kind of the things that what you really want to do at the time of the test. So I said this is kind of a very noisy question, but you have to get used to things like this. All right, the bottom one is also, I really want you to think about. Most of the time, people think that, okay, there are reagents here, written top or bottom of the arrow. And then yes, we do have a reagent there. It's called the DMF. That's shown here. So DMF, and you see here, yeah, that's an iodine here. That must be leaving. So it kicks out, make the bromine, iodine goes out, DMF goes there. Is that the right answer? I mean, that may be right, but you got to think about what is DMF. It's not the atom, right? There's no atom name is DMF. What is a DMF? This is something that I ask you to at least memorize it. That's a dimethyl formamide. That's a solvent. That's an aprotein polar solvent that makes an SN2 reaction goes well. That's a solvent. What's a solvent? Doesn't normally participate in reactions. So that is not correct. So if you really want to know some of the acronyms of the chemicals, like an NBS, I mean, that's a bromination reaction. We talked about the NBS makes the bromine solutions. It can be used as a source of the bromine for the free radical chain reactions. And the type of exam, when you write an NBS, you just have to know what it is. Because if you ask us, we're not going to tell you what it is. You have to know. Just like a BMF, that's the dimethyl formamide. These are typically solvents. So this is not a nucleophile. But we got the living groups. So where's a nucleophile there? Where's a nucleophile? Well, somebody may thought that, oh, maybe the sodium, maybe that's the one that makes an attack. Sodium makes an attack and then kick the ions out. So I got the sodium sitting on there. Is that right? But this kind of doesn't make any sense because why this nucleophile makes an attack? Because you got the partially positively charged carbon here. And then you're hitting that with a positively charged the sodium, that positive, they repel. They don't get attracted. So this is not the right nucleophile, right? So then what's a nucleophile here? Then you have to pay attention that why next to sodium, we got oxygen negatively charged. That is a nucleophile. It just happened to be connected together with the carbon chain. But this is a nucleophilic end. That's the living groups on the other side. This is like a snake biting its own tail. What happened was this oxygen, negatively charged oxygen, that's a nucleophile, makes an attack to this carbon because we got the living groups right there. It's making cyclic structures. It closed the ring. How many sides of ring? 1, 2, 3, 4, 5, 6 member ring. So you get the 6-member ring forms right here with the oxygen. This is a carbon, this oxygen right here, one position, and then this carbon number 6, that's the one that where the iodine was. So that makes an attack to there, close the ring. So this bond is what we just made it. There's the where the iodine just left out. So that's something called the intramolecular reaction. Reaction happens within the molecule. It's kind of SN2 reaction, kind of hidden there, because normally you are accustomed to see 2 molecules, one alkyl halide, another molecule becomes a nucleophile. But because they got connected, we only give the 1 molecule, so you got a little bit disoriented, but this is not the form you normally see in the question.